Listen to this closely. Your code might pass every single unit test. It might run perfectly on your local machine. It might even run fine in production for years. But if you have missed just one tiny synchronization detail, your application is technically broken and could crash at any random moment. Scary, right? Today, we aren't just writing code. We are going to learn how to stop your data from getting corrupted when thousands of users hit your server at the same time. Hello friends. Today we are cracking one of the toughest topics in software engineering, thread safety. A lot of students and even experienced devs think thread safety is just about slapping the synchronized keyword on a method and going for a chai break. But that is actually a recipe for disaster. Either you'll have bugs or your app will become super slow. In this video, we'll understand what exactly is a thread safety and how to correctly synchronize your threads without killing performance. So grab your notebook, let's clear the logic. Let's dive in. Okay, before we talk about logs, we need to understand what we are actually protecting. We often say we are protecting code, but technically we are protecting data from uncontrolled access. Imagine you have an object. Its state is basically its data variables stored inside it. Now, if you have a variable that is shared, meaning multiple threads can touch it, and mutable, meaning its value can change, you have a problem. If two threads access a variable and neither of them writes to it, we are safe. But the moment one thread tries to write or modify that data while another is reading it, they must coordinate. If they don't, you get data corruption. Here is a pro tip for you. Stateless objects are always thread safe. Why? Because if an object has no state, two threads can't step on each other's toes. It's like two people reading two different photocopies of a book. What I do to my copy doesn't affect yours. But when we share state, that's when real drama begins. Let's look at a classic bug, race condition. Race condition happens when your code's correctness depends on lucky timing. If the timing is bad, the code fails. Look at this buggy singleton design pattern to create a new object. This is a very common pattern called check, then act. Now imagine thread A comes in. It sees instance is null, but before it can create the object, the operating system pauses thread A. Now thread B comes in. It also sees instance is null because thread A hasn't finished yet. Both threads will create a new object. If this object was supposed to be unique, you have just broken your application's logic simply because thread A was bit slow. This depends entirely on scheduler, which is unpredictable. Now you might be thinking, okay, but simple math is safe, right? Like count plus plus. Wrong. Even a simple increment operation like count plus plus is not atomic. It looks like one line of code, but the computer actually does three things. fetch the current value, add 1 to it, write the new value back. This is called read, modify, write sequence. If two threads do this at the exact same time without protection, they might both read the value 99, both add 1 to it, both write back 100. You expected 101, but you got 100. You just lost the data. So how do we fix this? We need to make these compound actions atomic. Atomic means indivisible. Either the whole things happen or nothing happens. We need to ensure that while one thread is modifying the state, no other thread can touch it. In Java, our primary weapon is synchronized keyword. Either you use synchronize method or synchronize block. This uses something called intrinsic lock or monitor lock. Every object in Java has built-in lock. When you use a synchronized block, the thread acquires that lock automatically. It acts like a mutex, mutual exclusion. Only one thread can hold the lock at a time. If thread A has the lock, the B wants it. The B has to wait, or you can say B gets blocked until thread A finished. If thread A never lets go, thread B waits forever. This ensures that only one person is changing the variable at a time. Now here is the concept that interviews love to ask. Reentrancy. Imagine you are inside a synchronized method and you call another synchronized method on same object. Will you get blocked? You already hold the lock, right? But you are asking for it again. If the locks weren't reentrant, you would deadlock yourself. You would be waiting for a key that you already have in your pocket. But the Java locks are reentrant. This means locks are tracked per thread and not per invocation. So here, when thread A calls this method, it gets lock on this object, and inside this method, when it calls the super method, the lock counter get increased. The JVM sees, oh, this thread already owns the lock and lets it pass, just incrementing a counter. This is super important when you have subclass overriding a synchronized method in calling a superclass method. Remember, locks are tracked per thread and not per invocation. Okay, so we just add synchronized to every method and problem solved, right? No, absolute nightmare for performance. If you synchronize everything, your multi-threaded high-performance server becomes a single-threaded queue. Only one user can work at a time. Let's look at performance. If you have a long-running operation or waiting for network response, you should never hold a lock during that time. Other threads will just sit there freezing. You need to narrow the scope of synchronized block. Check out this code structure. Instead of locking the whole method, we only lock the tiny part where we actually touch the shared variable. By doing this, we keep the code thread safe, but still allow other threads to run while we do the heavy match. We are balancing simplicity with concurrency. The synchronize keyword in Java can be applied in 4 different contexts to control thread access. Let's break each one down with clear example. Synchronized instance method logs on current object, that is this, which is owning the method. Only one thread can execute any synchronized instance method of that object at a time. Second, synchronized static method logs on class object, that is dot class object. Since only one class object exists per class, only one thread can execute inside static synchronized method in the same class. Third, synchronized block inside instance method logs only a specific block of code within an instance method. You can choose a lock object, this or any another object, to avoid external interference. And fourth, synchronized block inside static method locks a block inside static method. You typically lock on class object again. Java synchronized blocks provide two happens before guarantees. One on entering the synchronized block and another on the exiting the synchronized block. I have covered both of them in depth in previous video of this concurrency series. I highly recommend you to go over that if not done already. Do understand how Java synchronized blocks provide visibility guarantees. So to summarize the golden rules, if variables are mutable and shared, you must synchronize to make them thread safe. Race conditions happen when you have compound actions without atomicity. Don't lock huge sections of code. Keep your synchronized block short. Designing a class to be thread safe from the start is much easier than trying to fix it later. So next time you write any Java class, ask yourself, is this safe? If you found this video helpful, please give it a thumbs up and subscribe for more technical content.